Good afternoon to everyone, and thanks a lot to Lucio and Cristiana and for their teams for organizing this special event. And for us, it's especially a pleasure and an honor to be able to present our work under this stand. When we were first invited to join this colloquium, we immediately thought about presenting a work that we have been developed in the past years, and especially a comparison between three protagonists of form finding, and especially physical form finding, to just try to place Frei Otto's contribution, or better, the contribution of the Institute of Lightweight Structures within the history of engineering of our last century, between analog and digital form-finding models. So we can start our presentation with a very simple observation about these three figures who are considered, or conventionally considered, together when we speak about physical form-finding. They were all three structural designers, even though Frei Otto was officially a German architect, Isler officially an engineer, and Sergio Musmeci also an engineer. But what is interesting is that they were all born in the same years, and their education was rooted in the engineering culture of their time, and their methods were informed by their individual backgrounds and scientific cultures. Even though they all advanced experimental approaches to the discipline of structural design, they represented different perspectives on form finding, and they all worked in the period that saw the transition from physical to digital models. For this reason, what to us was most interesting was not the exceptional works they conceived, but rather the inspirations, the methods, and the visions they developed with different techniques, objects, and people. And this is how we structured our presentation.
So starting with the inspiration, of course, inspiration for all. Otto, Isler, and Musmeci is nature. And nature is a source of inspiration in order to design structural models and buildings that are going beyond the classical typologies. Well, in this specific case, we need to acknowledge that each of these three protagonists are looking at nature in a slightly different way with different conceptual lenses. For Frei Otto, for example, biology and biological processes are what is a trigger for new structural forms. In 1961, Frei Otto established a new research group, Biologie und Bauen. It is very much rooted and very much developing research about biological processes, processes about self-formation and self-organization. In the view of Frei Otto, each element can be considered as develops as an interplay between tension, compression, bending forces. In the case of Isler, nature is a formal reference, and a reference that is for the designer and is supposed to trigger the imagination of the designer. So forms found in shells, insects, and plants reflect principles that are shaped by physical necessity. And well, this clarity of this form, in fact, provides some valuable guidance for creating efficient structural solutions. It's very interesting to see also that Heinz Isler is using this resemblance between the shells, the concrete shells that is building together with shells that we can find in nature as a way also to advertise and promote his own work, and in this way to really be able to communicate his work on multiple levels and a very broad audience. Unlike Otto and Isler, Musmeci looks at physical phenomena through a very mathematical lens. And in fact, he sees form as the way how matter is organized in space. This is very evident in these studies, as we see in this slide here, about organization of crystals, elements in space, polyhedra, antipolyhedra, or for example, in these studies about how to organize antiprismatic systems in space that have, of course, inherent structural qualities.
And while Otto, Isler, and Musmeci consider different inspirations for their design processes, the methods they adopted were even more diverse. Because how we have already seen in previous presentations that Otto considered really the physical experiment as the primary source of knowledge. And among the three protagonists of structural form finding, he's probably the one who explored the most with every material, type, and principles. But actually, unlike Isler and Musmeci, his design approach resulting from strong collective research that brought together several disciplines at the University of Stuttgart. And they all gather here in this building for research meetings, conferences, and spontaneous discussions. The design was therefore the outcome of not only one person, but it was the outcome of many discussions and prototypes that were developed together. They were geometrically measured and then controlled up to the final construction. In contrast to Otto and Musmeci, who explored several types of structural form, Isler devoted his work to study a very specific typology, which was the reinforced concrete shell. And this picture is quite famous because it was the way through which Isler promoted his new shapes for shells, proposing endless possibilities of freeform shells that were based on the use of many physical models across the design stages. But if Otto's Institute of Lightweight Structures employed very sophisticated models with experimental machines, the materials employed by Isler's office for the form-finding physical models were simple and economical, enabling Isler and his collaborators to test several design variations in the form of plaster models until the most appropriate shape was found. And this was also mirrored in the organization of Isler's office, where the physical models really played a central role in the layout of the office itself. The model makers supported Isler in the construction of the physical models and in the evaluation of the found geometry with a very rigorous protocol, with a handcrafted measuring machine to extract the shape coordinates. And the structural performance was then tested in a nearby room in the office, in the model testing laboratory, where engineers and draftsmen studied a fiber-reinforced polyester model under different load conditions with electrical resistance strain gauges. Something that was later translated into a digital procedure with mainframe computers to save time on repetitive processes.
So when it comes to Musmeci, Musmeci thinks that the optimal structure should necessarily explicitly show the distribution of the internal forces. For him, the form is the unknown, not the internal stresses. So his mathematical approach is very much driven by this philosophy, and this approach to structural design is very based on mathematics in general. So we see here, for example, this study for a new roof, a folded plate structure for the Stabilimento Raffo in Pietrasanta that has been eventually built. And well, in this case, Musmeci set it up a parametric model made of a system of equations that can be used in order to explore different design variations. Each equation is representing one folded edges in the structure. But most likely the most representative project of Sergio Musmeci is the Basento Bridge in Potenza. And this is very much also showing a representative of how Musmeci was working in terms of the use of physical models, how these physical models were very much related also to analytical models. So we see here the initial conceptual phase of the design with subfield models that were used in order to visualize mathematical minimal surface that then was analytically derived, as we see on the other side of the slide. Another model was subsequently used in order to define the geometry of the structure in a more precise way is this neoprene model. So in this case, again, using the principle of the minimal surfaces and building up a physical model to be able to cache the geometry of the structure. And then this was then graphically represented after measurements of the model. Eventually, another model here, a metacrylate model. This was a model that was used in order to assess the distribution of the internal stresses in the structure using electrical strain gauges. And we see, very interestingly, on the other side, the use of numerical methods for evaluating and defining the geometry of the structure in a more precise way using the finite difference methods, and in the center of the slide on the right, we see even a model that is derived from the use of a computer program. This was built and designed actually after the actual bridge was built. Then eventually the last model is this one, this 1:10 microconcrete model that was built at the ISMES laboratory in Bergamo and was used in order to make a final assessment of the structure, loading until collapse in order to evaluate the maximum capacity of the structure. And in fact, this model was also used in order to, as a basis for the actual design and construction of the real bridge at the end.
And as we said at the very beginning, all three of them witnessed the shift from physical to digital models, and all three of them used the computer in very different ways. Because if either physical or digital models could exploit the control of the structural behavior, the creative aspect of the design was more difficult to translate into a computer. And this is the aspect for which all three of them envision new types of collaboration between analog and digital models. For this reason, with different approaches and at different times, Otto's research group, Isler's engineering office, and Musmeci try to translate their physical models into the computer. On this transition, we are currently then working further. Unlike Isler's office, the EL managed to find a balance between analog and digital models, especially in the early phases, the work was mainly done with physical models, and only at a later stage, it was supported with emergent computational tools. And this is quite visible in the famous project of the Munich Olympic Stadium, even though during the competition, the only engineer involved was Heinz Isler and not Fritz Leonhard or structural designer Frei Otto, where basically the form of the physical model was compared with that one generated with early digital tools, thanks to the really strong network among the different institutes at the University of Stuttgart. So it is no coincidence that Linkwitz and Scheck developed a computational approach to control the geometry of the complex cable net structure and compare it with the photogrammetric measuring model based on the geometry developed by Otto's team. Or that Argyris with his team developed a computational method to define the shape of tensile membranes. But contrary to Musmeci, Isler thought always that computers cannot provide creative results as physical models do instead. However, he was one of the very first ones who pioneered computational methods to reconstruct the shape of his pneumatic models already at the end of the 50s, thanks to the collaboration with the Institute of Applied Mathematics at ETH Zurich, working on one of the very first mainframe computers ever built. Later, the office progressively started to adopt early digital models to evaluate structural performance as an alternative method to measuring physical models. However, Isler's long experience with physical models made him question the use of computational tools in some design projects, and especially in the Stuttgart project. In his opinion, the apparent simplicity of the computational process can lead to arbitrary outcomes, especially when implemented without any experience with physical form-finding techniques.
So, well, unlike Otto and Isler, the approach of Musmeci to the use of computer is quite different. In fact, Musmeci is envisioning a possible interaction between the human designer and the machine to enhance creativity in structural design. So Musmeci writes, it is evident that the computer can be of great help in the verification phase. However, it is equally clear that only if a way is found to use it from the initial stages at the service of the designer's inventive capacities, will it truly contribute to the exploration of creation of new, more efficient structural forms. I believe that one day, perhaps not too far in the future, this will be becoming the standard approach for the creative structural designer. Automatic computation, far from limiting their imaginative possibilities, will serve as an effective support tool and a powerful means of amplifying their impacts on the built environment. It's really evident that Musmeci is envisioning the use of computer to create new structural forms, find efficient structural forms, but also going beyond the classical standard topologies for structure, as we can see in some of his projects, like this cable network for the roof, for the proposal of the new sports center hall in Florence, or for example, this project here, probably the most visionary projects of Sergio Musmeci, that is a proposal for the bridge over the Messina Strait with a free span of 3,000 meters. Well, Otto Isler and Musmeci pioneers new approaches for form finding, reshaping structural engineering through their cross-disciplinary curiosity and innovative methods. They left behind an extraordinary legacy. Also, through the remarkable ILEK archive here, rich with models, tools, publication, and of course, also numerous build projects. Isler, with an extensive collection of models, publications, writings that are all preserved at the GTA archive at ETH Zurich, along with many realized projects as well. Musmeci, through his influential articles and books on form-finding theory, as well as the collection that is housed at the Maxi archive in Rome. Their methods, of course, laid the groundwork for today's computational form-finding, and we are all very much glad that we have this legacy from these fantastic structural engineers and architects, and this will definitely continue to inspire very much us and also the new generations. In fact, as Isler noticed, what is the best form or even the correct form, this will remain the crucial question. Thank you very much.